This is Official Nerd Business. Hello nerd boys and girls, welcome back to our regular programming. Today we'll take a look at Euler problem number 20, and as you can see I've already created the template file. So here is the description, here is the method that allows us to run this file on its own, here is the method that will be called from the main by, which I've got open over here, and here will be the logic to solving this problem. What specifically is problem number 20? Factorial digit sum. N with an exclamation mark, or n factorial means n times 1 less than n, 1 times, eventually you'll get to 2 and to 1. Why we do times 1, by the way, I'm not sure, but whatever. For example, 10 factorial is 10 times 9 times 8 times 3 times 2 times 1 is this number over here. The sum of the digits in this number is 3 plus 6 plus 2 plus 8 plus 8 plus 2 zeros, again 27. Find the sum of the digits in the number 100 factorial. We take one parameter n, so by default this is 100, and we are to calculate the factorial for this number and sum the digits. So with step number 1 we get n in as an input here. So the factors of the number that we want are in the range from 2 to n plus 1. Remember that the upper bound on range is 1 less than the actual number put in. And now we can multiply this. I've already added one import statement for our Euler library because we have a product of list function in our Euler library. So if you put in the factors list, it's going to multiply every number on this list. And now we want the digit sum. So we want to return the sum of I think this should work. Oh, hang on, I've misplaced one bracket here. There we are. So we make a string out of whatever our product is. Then we map an integer function over it. This should explicitly break this down into its individual digits, because under most circumstances Python will see strings as a list of characters and the map function maps over lists. The map will return a map object, so this needs to explicitly be converted back to list, and we take the sum of that, giving us our answer. Now if I were to make the default parameter 10 here, we should get the 27 from the example, and we get 27. Mike, that's amazing. So let's run main by, and we want the answer for problem number 20. The default parameter is 100 and the sum is 648. I can tell you, spoiler alert, if you enter this over at Project Euler you will get the green check. Are there any other ways of doing this? Maybe. One such method is importing the math library. Because the math library by default has a factorial. So we could do all this again, except the part where we calculate the factorial. We don't do our own calculations here, but we simply say I've given this math library the abbreviation M, but we could drop it and then expand this all the way up to math. The PEP style rules require me to have two enters around or before a def statement, a function definition. So this should be identical, except maybe slightly faster. Well, it's hard to get much faster than zip.zip, of course, but generally this is a slightly faster method than doing this. So if I again run mainpy and tell it to return attempt number 2, yeah, this is no time whatsoever, and the answer is still the same. So the built-in factorial method works just fine. There is of course a way to solve this with recursion, but with very big factorial numbers you might hit recursion depth limit, so the number of times a function can call itself. So I'd advise just using the built-in math factorial whenever we use factorials, and we will be seeing factorials a lot in the future. They appear to play an important role in statistics and combinatorics, and we will see some problems in those domains. So yeah, that's problem 20. It's a bit of a short video. But to counteract that, I want to take us one step back and look at problem number 19 again, because I was pretty happy. This one was the one where we counted the Sundays at the number of months in the 20th century starting on Sundays, and we had three attempts actually. First we counted off all the possible, all the actual days of the month. Then we started creating date objects, and then we threw some statistics at it. I saw a different method on the internet, which I found very elegant, and I wanted to show you. So here's attempt number 4. Again, not taking any parameters because there are no variables in this case. There's no small test case or whatever. There's just this date range. And the date range is exactly how this answer is going to work. It's going to use dates as well as our second attempt here did. But it's going to do so slightly more Pythonic, if you will. So what we need for a date is are 3 parameters: the year, the month, and the day. Now the day is always fixed to 1, the first of each month, but the months and the days, or the months and the years, excuse me, are what's interesting to compute, to run a loop over. And now here we are incrementing all of this by ourselves and keeping track of year rollovers and all that. We can do better than that. If we were to create a list with all the parameters that we are interested in, we could simply create a list of tuple elements where we specify that the values in that tuple should be generated out of this range, and again out of this range from 1 to 12, or 13 in fact, because we do want December. And then I will print to show what this does. So yeah, this is a very cool and Pythonic way of setting up our parameters. We aren't actually creating dates yet, but that will come in a second. But as you can see here, we are basically generating a list with all the parameters that we need to create a date. namely years and months in given ranges, and always the first of that month as the day parameter. So if we were to run temp number 4 and simply print out everything, switch this to A4, run this particular file, here you can see all of the date parameters. So it first lists of all the months in the year 1901, and then it will take a look at the end here. You can see it creeping up to the year 2000 and January, February. So all of our dates definitions are in here, so let's create actual dates. And we again use these list symbols to create a list comprehension, or to simply generate a list out of the pattern that we define here. So here you can see that the parameters actually create dates. So what we say here is create a list. These square brackets define that whatever is in between them will generate a certain list of datetime date objects instantiated by year, month and day, where we get those values as a tuple from the list date params. So in the previous step we created a list containing 1933, a 4 and a 1, and 1933 and a 5 and a 1, etc. Everything up from 1901, 11 up to 2001, 12, 1. And for each of that set of starting parameters, a date is now created. And we can put another generator around that, like so. Now we put in every date that we find. This is now basically an input list for the second generator around it, and it takes every date it finds and put it into our list of dates. But we can add a filtering criterion to this, because we are still only interested in the Sundays. So now it generates this date, and then it immediately evaluates if it is a Sunday, and if it is put in the second list generator, and eventually only that list generator will be assigned to dates. So if we would run this, then we would get this month apparently starts on a Sunday, December started on a Sunday, June starts on a Sunday in 1902, etc, etc. And the answer now simply is how many dates are on this list, simply the length of the array. And if we were to run this through main, that was pretty quick. If we were to fall back to, say, a temp number 1, we have 1, 2, 3 zeros and then a 9. And let's see if we were to, this one, no, 19, this one. If we were to switch back to temp number 1 and then run main again, it's also pretty fast, apparently. This might just take a little bit longer. No, it doesn't. Right, so performance wise it's pretty much the same, but code itself is way more concise, it feels way more the way we should do things in Python, and I very much like the elegance. So I did also want to show you this, and that's it for this video. And we will have a crack at problem number 21 in the next video. And I'd like to remind you to check out my GitHub, where you can find all of the source code for this project. Thanks for watching this video on Official Nerd Business. Don't forget to like and subscribe and click the bell icon. Did we discuss everything you wanted to hear, or did we miss anything? Any topics you want to hear in O&B? Leave your thoughts in the comments. See you next time.